Okay, so if you haven't seen the Piazza announcement, there's no class Thursday, but I will be posting a video lecture for Thursday. So you're still going to be responsible for watching that video lecture. Essentially, it's going to be a video lecture from last spring, and it will go over the introduction to AVL trees. So I will expect you to come to class next Tuesday having already watched that video lecture, because we will be going into whatever material is down for next Tuesday. The reason there's no class, was an ABET conference this week. ABET is the accreditation agency for the engineering college. Every 6 years it comes to campus, spends a day here evaluating each of the engineering programs. And next year we prepare what is called a self-study document in preparation for their visit in 2017. And I am the chair of our ABET committee for the EECS department. So I'm going to the ABET conference this week to learn more about the procedures that they use for these visits and for putting together that self-study document. So I'm leaving pretty much straight after class. So I'll be, after seeing one student, essentially flying out of here. So I don't have office hours this week. This TA still do have office hours. Notice that the department grabbed the conference room where the Friday office hours are normally held, so they'll be held in Min-K 416 this semester. I'm sorry, this Friday, which is also known as the Programming Clinic. You can post, of course, messages to Piazza. I will monitor that, although it may well be just once a day, so you won't get very fast feedback on Piazza, but still TAs will be there. Had a question about the speed of Shapeshifter, how fast it needs to be. Dr. Plank wrote that his took about 42 seconds. It should take no more than 3 seconds to run the entire grade script. So if your Shapeshifter stuff is taking more than 3 minutes, that's bad. If it's taking less than 3 minutes, that's good. Okay, but it won't. Not every test case will run instantaneously with Shapeshifter. Okay, that's part of why he wrote it. Was he couldn't always, or he wanted to be able to get the solution to these problems. So, questions about that? Okay. So, today we're going to give you a couple exercises with doing deletion in binary search trees. Make sure you understand it, and then we're going to go over the code that is used for implementing binary search trees. And just as a quick reminder, binary search tree, every interior node has at most 2 children, and for any node in the binary search tree, all children to the left have a lesser value. So for each node in, and I'll abbreviate it BST for binary search tree, okay, all nodes in its left subtree have a value less than its value, and all nodes in the right subtree have a value greater. And if you allow duplicates, then you just arbitrarily choose to put those duplicates either into the right or the left subtree. We've been dealing with trees that have unique values, and the code assumes also that the keys are unique. But if you want to have a multi-map, remember that what is a multi-map can have multiple keys with the same value, then you just arbitrarily say that all duplicates either go into the right subtree or into the left subtree. Okay, so doing a insert is pretty simple. You simply follow each node, either left or right, depending on the value of the inserted value, until you reach a place where there is no child and where it can go. So for example, if I want to insert Maggie into this tree, I would go to Fred because Maggie is greater than Binky. Then Maggie is greater than Fred, so I'd go to Luther. Then Maggie is greater than Luther, so I would go to Waluigi. And Maggie is less than Waluigi, so I would end up putting Maggie as the left child because Waluigi doesn't currently have a left child. Okay, finding, also very simple. If I want to find Luigi, start with Binky. Luigi is greater than Binky. Luigi is greater than Fred, so I move to the right. Luigi is less than Luther, so I move to the left. There's Luigi. Okay, so find and insert, pretty simple. Delete, little more complicated. So there's three cases. Case one is it's just a leaf like Callista, which case we just delete it. Case two is it has one child like Daisy, in which case we simply promote its one child to replace it. So those are two easy cases. The hard case is something like Fred, where you have two children. In that case, you find the greatest value in the left subtree, which in this case is Daisy. And if you remember, if we find the greatest value in the left subtree, it cannot have a right child. Why? Because then it would not be the greatest value. If it had a right child, the right child would be greater than it. It's like a proof by contradiction. Okay? So the greatest value in the left subtree cannot have a right child. Therefore, we have either case one or case two, which is really easy. So we already know how to do case one or case two, so we recursively call delete on that node, which is Daisy. And once we've deleted Daisy, we move all the information associated with Daisy to Fred's node. So in this case, after deleting Fred, Daisy would be here, and Callista would have moved up like that. Okay? And just think for a moment, what would happen if instead we deleted Luther? What would the tree look like after I deleted Luther? Todd, give you a try.
Luigi take the place of
Very good. So Luigi is the greatest or the biggest value in the left subtree. So we delete Luigi and then we move it up. So Luigi moves up. Okay, so it's time to try your own. So I got two exercises for you. So in this one we are deleting John. So try to delete John from this particular tree. These are great problems for the final, by the way. Like, guaranteed to be on the final. Go ahead and branch out. Man in the glasses, what is your name? Hazib? Nasib. Nasib. So what is the solution? Jill will replace John. Very good. So since John has only one child, Jill gets promoted, John goes away, and Jill is now the new right child. Questions about that? Okay. A little more complicated. Now we delete Laura. She just so happens to be the root of our tree. And Ashley, what do we do here?
John will replace Laura.
Very good. John and Jill gets promoted. So two things happen. So John is the greatest child in the left subtree, so John's going to get promoted to replace Laura. And when we delete John, Jill will get promoted. So Jill comes up and John gets promoted all the way to the top. So if you're still not sure, read this caption. I won't read it to you. So questions about this? Okay. So let's go over the code, because what I find is it's a lot on tests. Students are very good at reproducing these things, but when it gets to the code, things get a little dicier. So let's start by looking at the .h file. And there's two classes, the BSTree class and the BST node, which is a supporter class. So each node of the tree, you can see, has a left and a right child. Now that could be null if well, actually it won't be. We'll get to that in a moment. Could be null if the child didn't exist. You'll see we're going to use a sentinel node, so that will factor into it. Then we also have each child point to its parent. Remember, in a tree, every child has exactly one parent except the root. The root is the only node not to have a parent. And then the key and the value that we're storing. Now, notice that it is a void star that we are storing as the value. This gives us a lot of flexibility because a void star pointer can point to any object. So the void star is the most general type of pointer. We call it, in effect, an untyped pointer. So usually pointers are typed. It's int star, or it is string star, or it's personnel star. But void star is essentially saying that it's untyped. It can be any type of pointer that we want, which gives us a great deal of flexibility. In the STD, the standard template library, we actually use a template to say, or type parameter to say what type of value is being stored. But we don't want to get real complicated with templates. It turns out that creating a template class involves some complicated syntax. So to simplify things, but to still try to make us somewhat general, This is an old C trick that allowed you to at least store a pointer to any type of object in your tree. Okay. Now the key still had to be a string, so that limits its flexibility somewhat. Then here are our public methods for our BSTree. So the BSTree is our container object. Okay, so this is the container object, which will contain a pointer to our tree. So you can see the public methods include a constructor and a destructor. That's what these two are. We want to be able to insert a key value pair. We want to be able to find and delete. Then we want to be able to print the tree, pretty print it, you'll see how in a moment. Return its size and whether or not it's empty. So 1 for true, 0 for false. This is Dr. Planky's old school. He uses C integers. Probably would be better if it were empty were declared as a bool, but be that as it may. And then sort it returns a vector of values. That's why the void star. And the values are sorted by key. So the keys are stored in alphabetical order, so the sorted vector is going to store the values in alphabetical order. And that's actually not a function, that's an actual vector that is public. Okay, but will only be up to date. I'm sorry, that's not a, it is a, I take it back, that is a function. Okay, now protect it. We have 3 instance variables or 3 member variables. So we're going to use what's called a sentinel node. So our container object, you can think of our container object conceptually as looking like this. And the sentinel is going to point to a sentinel node. That's not going to have any value in it. And by default, or convention, the first value in our tree, let's say is Binky, will be the right child of the sentinel node. The sentinel node has no value. So we just conventionally say that the root of the tree is the right child of the sentinel. Okay? And it's going to transpire. The sentinel has some nice properties. One is that we're going to make all of the children that are leaves are going to point back to the sentinel. So Alfred is a leaf node, and in fact its left and right children will point back to the sentinel node. So all the children are going to point to the sentinel node. And this will help us out somewhat as we go along. It can sometimes help simplify our algorithms. When we dealt with lists, the sentinel node eliminated the additional code of checking whether we were at the front of a list or not when we did certain operations like insert. We didn't have to worry with the sentinel node whether we had the special case of the front of the list or not, or the special case of the end of the list. The sentinel node performs a similar function in a tree, as it's going to allow us not to have to worry always about what happens with special cases, like perhaps if there's no node in the tree yet, although in this case turns out we will have to worry about it. But I'll show you a couple tricks you can do with sentinel nodes. We keep the size, and then this vector here is the one that's going to keep track of the sorted values. Now, we're not going to keep track of it all the time, but only when we call the function sorted vector are we going to actually worry about filling this vector. And then finally, we have some helper functions that we don't want to be public, and we will get to those. So The print function will use the in-order print recursion. The sorted vector will use makeArray. And the destructor is going to use the recursive destroy. So you'll notice that these are all recursive functions. So back last week, I said that in order to deal with tree algorithms, we had to introduce you to recursion. Well, this is why, because we are going to have some recursion in dealing with our trees. Okay, so for this particular project or lecture, Dr. Planck came up with a person class, and that is going to have a name, and then you're going to insert a pointer to a person. Now, Dr. Planck shows you doing this by inserting Fred and then having this cast of the pointer to a void star. And he says if you don't put the void star in, the compiler will yell at you. That's not true. Okay, it turns out that because void star is always acceptable where a type pointer is, it will not yell at you. You could, in fact, not put void star here, and it would work just fine, and the compiler would not yell at you. In fact, I won't yell at you. Okay, but the reverse is not true. If you have a void star x, and you have a person star p, and you try to say p equals x, now the compiler will yell at you. Because void star is untyped. Void star can point to anything. It doesn't have to point to a person. So if I wanted to do this operation, I would have to say person star to indicate that the void pointer should be pointing to a person. But I'm allowed to say x equal p without any problems, because void star is more general. So here the p is more specific and the void star is more general, so that's allowed. Okay, if you want an analogy, watch this with numbers. So okay, so if I have a int x equals 6 and a float y, if I assign x to y, would you expect the compiler to care? Okay, because I'm not losing any precision, right? But let's say that instead I tried to assign y to x. Do you think the compiler now might care? Because I'm losing precision, right? I have to truncate y, so I'm losing precision. So with the second assignment statement, the compiler might give me a warning or an error message. The same holds for pointers. Okay, a void star is very general, but a person star is more specific. So if I say x equals p, it's a void star is like float. Okay, and person is like an int. So when I assign a more specific thing like p to x, there's no loss of precision. But when I try to say p equals x, there's a potential loss of precision there. X could point to anything. There's no guarantee that it points to a person. So I have to guarantee to the compiler that it points to a person by putting the cast in front of it. Okay? So hopefully that, any questions about that? Okay. Okay, so he wrote an example program, and here is his class is going to have a name, a phone number, and a social security number. And he wrote a nice little editor for us, so we can actually invoke it. So let me actually do that. Okay, so his editor is BSTree test, and if you give it a dash, as is most of his editors, there we go. So now we can do some things. So here's a bunch of inserts that I'm just copying. So it does all those inserts. Now I can print, and it's going to do a pretty print. So he's printing it so that if you rotated it 90 degrees, that it would look like a regular tree. So there he does it. He says, here's our tree. We rotate it 90 degrees, and it kind of looks like the tree over there. You can argue whether it does or doesn't, but at any rate, Binky, if you look at it, Binky was our first thing that we inserted, so it makes sense that Binky's the root. Then we inserted Fred, so Fred should be the right child of Binky, and it is. Then we inserted Luther, and that should be a right child of Fred, and it is. Then we inserted Waluigi, which should be a right child of Luther, and it is. Daisy should be a right child of Binky, which it is, and a left child of Fred. There it is. And you can do the rest hopefully on your own. So print's just doing some nice pretty printing. Okay, so let's insert Alvin. And we'll give Alvin's. Okay, and if we again do a print, Alvin should be where? If this was our tree right here with Binky being the root, where should Alvin go? Left of Binky. There is Alvin. Okay, let's say that we delete Binky. What should be the new root of our tree? Alvin. Because Alvin is the only child, there it is, only child in the left subtree. Okay, so enough playing around. Actually, let's see, did he give us anything more? Delete, print, quit. Those are only commands. Sort. Let's find Callista. So it returns the information associated with Callista. If I try to find Brad, not found. If I sort, it returns them in sorted order by name. Okay? So he starts with just the code for his editor. And it can't hurt to know how to read his editor code, because sometimes when you're debugging your code, you need to know how his editors work. What he typically does is he reads in a line and he breaks it into a vector of individual words, which in this case he calls it SV. Not always sure what his abbreviations stand for. So SV, at any rate, is a vector that takes a line and breaks it into words. So he's looking at the command, which in this case he's saying if the command is equal to insert, then insert expects to have 4 words on a line. It minimally needs to have insert, a name, a phone number, and a social security number. Now you're allowed to have multiple names, so I could actually run it again. And I could insert Brad Vanderzanden. Okay, and it works. Okay, And so what his code is doing is then it's saying there can be an arbitrary number of words on this line, but he always knows that the last two are the phone number and the social security number. So he's saying that as long as I have a good line, if I don't, he prints an error message. Otherwise, he creates a new person and starts by assigning the first word to name. Then he continues to append names to it as long as he hasn't gotten to the last two elements of the line. Then he knows that the last two elements of the line are the phone number and the social security number. So when he exits this for loop, I is going to be pointing to the phone number. That's why he can say equals SVI. Finally, he tries to insert, and if that name is already in there, it will fail. So insert returns true if it succeeds with the insert and false otherwise. If it failed to insert, it says it's not inserted and it deletes it. Why does it delete P if he failed to insert the person? What would be the name of what name do we use if he forgets to delete P? Pardon? Memory leak. Yes, he would have a memory leak. It would not affect the ultimate correctness of the program. However, he would have a memory leak, and if this was a long-running program, he ultimately might run out of memory. Okay, so onward. So the implementation, not a big fan of how this looks. So if he inserted Fred, Binky, and Luigi, what he really has is something that looks like this. The Sentinel node will point to that, or the Sentinel will point to that, and that will point to Fred. Fred will point to Binky and Luigi. And then both of these, left and right child, will point back to the Sentinel node. Okay, that's what's happening. If you look at his code, or not his code, his figure, it's the same thing. So if we look at, this is the Sentinel, it points to something that has no value. You can see its right child points to Fred. There's Fred right here. Here's Fred. You can see Fred's right points to Luigi. You can see that Fred's right points back to the Sentinel node. Same thing with Fred's left. Okay, and then Fred's value, or Luigi's value, points down here to a person object with Luigi's information. Okay. So that's how we go. So now let's go to insert. Oh, first, size and empty are easy. Size returns the size. Empty returns whether the size is 0. So if it's equal to 0, that will return a 1. Otherwise, it returns a 0. Here's the constructor. We create a Sentinel node, set the parent and left to null, make the right point to itself, because right points to the root of the tree. Currently, the tree is empty, but it's important that it points to itself. And then we set size to be 0. So pretty simple for the constructor. Okay, find is the easiest function to implement. So we start by getting the root. So the root of the tree is pointed to by the Sentinel. So this gets the root. Okay, so get the root node. Okay, so now, while we just are going to go into an infinite recursion, if we reach a Sentinel node, that means we've not found it. It's gotten to the very end. and the value was not found. Remember, every leaf node, its left and right child points to the sentinel node. So if we get back to the sentinel node, it means we failed to find it. So we return null in that case. Otherwise, we check to see if there's a match. And this is the found case. So the key was found. So return the value associated. Okay? Now, this is, by the way, I guess I'd never made this clear. We're using this to implement a map. Okay? We could also use this to implement a set. If we used it to implement the set, what variable would we subtract from this implementation, from the node? Not the key, the value. So if we're implementing the set, sets only store keys, so we would eliminate the value field. But the algorithms are pretty much the same regardless of whether it's a set or a map. There might be a little difference in that with the find we would probably simply return true or false rather than with a set we'd return true or false. With a map we return the value. Okay? If S is less than the key, we go to the left, so we set N to be left. So if S is left, go to the left child. And if it's greater than, we go to the right child. Pretty simple. And we are guaranteed to ultimately stop because if it's not in the tree, so let's see, here's the sentinel node, S, points to Fred. Fred points to Binky and Luigi. So let's say I search for Rachel. Whoops, and they both point back to the sentinel node. So if I search for Rachel, I go to Luigi. Rachel is greater than Luigi, so I go to the right child, which is the sentinel node. So I'm always guaranteed to exit this infinite loop. So it's actually not really infinite. So any questions about find? Pretty simple, right? Okay, so now we go to insert, which takes a string and a val. So again, we start, and what we're going to do is first we need to find the parent. So let's say again we had Fred. Here's our sentinel node. We had Binky, and we had Luigi. Let's say now we want to insert Rachel. Well, what we want to do is we want to find the parent node for Rachel. So that's what this first loop is going to do. And what we're going to do is we're going to keep a trailing pointer. So initially, parent points to the sentinel node, and N points to the root. Okay? Think about the advantage of that. Let's say that the tree was empty. There was no thing in it, so we'd immediately exit. What should be Rachel's parent in that case? The sentinel node, and the parent points to it. Okay? Otherwise, but in this case, we can see that Fred exists, so what happens is we're going to update N to point to, actually first we'll update the parent so that it's equal to N, and we'll move N down to here. Then we will again move to the right, except that will make N equal to what? When we try to move right from Luigi, where will we move to? The sentinel node. So N will now point up to the sentinel node, and we're going to make the parent point to Luigi. And because n points to the sentinel node, we know that's where Rachel should go. And because we've kept a trailing pointer, parent is a trailing pointer, parent points to the right place to insert Rachel. Okay, so that's what this loop does. While n is not equal to the sentinel node, okay, if we find Rachel, we want to return 0 because we don't want to store duplicate keys. So if Rachel's already in there, we get out. Otherwise, we set parent to n and then update n. Why don't we set parent to n afterwards? Why couldn't we do that? Kim, what would happen if, why can't I move parent equals n to the end of it? Is there any reason why I was careful to make it first? Okay. Do you know, or do you want me to move on? Looks like I should move on.
Is it because you changed n?
Yes. So I changed n, right? So if I update it down here, I would be pointing to whatever n currently points to. So for example, when n gets to be the sentinel node, I would end up with parent pointing to the sentinel node. So I have to do it here, up top, before I reset n. Okay, so order is important. Okay, so when I come out of this loop, and I'm right here, I know what the parent is, and I know also that I will be inserting it. So this code creates the new node and sets its. Why do we set its left and right to be sentinels? Because it can't have a child. It is a leaf. Very good, Jaja. So we know it's a leaf node, so we set its left and right to be the sentinel. We set its parent to be equal to the parent. So we've set it all up. However, okay, so at this point what we have, okay, so we have this point Rachel. So Rachel points back. Rachel also points this way. But what we're missing is what? What have we not yet done? Rachel points to her parent, but what does not point to Rachel? Her parent. So we have to link Rachel into the tree. Okay, so the way we do that is okay, we check, well, I'll get to this case in a moment. So if S is less than the parent's key, it should be the left child. Otherwise, it should be the right child. So in this case, Rachel is greater than Luigi, so we make Rachel be a right child of the parent. Okay? What are we doing in this case? What is this particular case covering? This is a special case. If the parent is the sentinel node, what is Rachel? I think I heard it. The root. So this is testing for an empty tree. Okay? So if the tree is empty, then the new node becomes the root. And in order to become the root, what does the sentinel, which child of the sentinel node points to the root? The right child. So we say sentinel right equals n. Okay, and then we say size plus plus, and we return 1 to indicate that the insert succeeded. Okay. So questions about insert. Okay, moving on, the tough one, delete. Okay, so the beginning is easy. It should be pretty familiar to you by now. So we just find the node. Okay, and we could almost use the find function, except that the find function returns the value rather than the node. So we actually have to duplicate our code here. We could, because this code is identical to essentially this code, or very close, we could try to write a helper function, but we won't. We'll just rewrite the find code. So this finds the node, and then this makes sure that we actually found it. Okay, if n is equal to the sentinel node, it wasn't in the tree, and we return false because we don't want to delete something that's not there. Otherwise, we're going to take a look at its parent. So again, let's say we had sentinel points to Fred, and let's have Fred point to Brad, and let's say we're deleting Brad from the tree. So the first thing we do, so n points to Brad at this point, and so we're making parent point to Fred. So that's the effect of this statement. Okay, let's skip, we won't, okay, actually we will. So first we check to see whether n's left is equal to the sentinel node, which it is. Okay, so we're checking, and in fact, that is the case. So this is case 0 or case 1. Right? Case 0 is it's a leaf node. Okay? So now we have to check, is it, I'm sorry, if it is equal to the sentinel node, then we replace it with its right child. So we don't really care if its left child is empty. It could be the case that this is Callista, but we don't really care. Either way, the right child is going to replace it. It's either going to be a sentinel node or it's going to be Callista. Okay? So in this case, there is no thing, so Brad gets eliminated, which means that Fred's left child is going to point to the sentinel node now. So right here, we're just checking to see whether this was Brad. We want to know whether this node is the left child or the right child. So this is asking, is the deleted node the left child or the right child? Okay, so if it's the left child, then we make the parent's left pointer point to the right child. And if it's the right child, we make the parent's right pointer point to it. Okay? So in this case, this code executes because Brad is the left child of Fred. Questions about that? Okay? Now, what we have to do is that, let's say that there had been a right child for Brad, and that was Callista. When we promote Callista, we have to reset Callista's parent pointer, right? Because Callista's parent is now what? Such thing. Stone. What is Callista's new parent?
I'm sorry, I didn't.
Okay. How about asking one of your two lifelines to your left or right?
He says Brad.
Nope, that is the old. What's the new? After I delete Brad, what becomes Callista's new parent?
Fred.
Fred. So I have to update. I have to make n's old right child, its new parent is equal to whatever n's current parent is. Except there's one case. If the right child was the sentinel node, we don't want to go and make the sentinel node's parent. We don't want to change the sentinel node's parent. So this handles the case. Okay, only reset the right child's parent if there really is a right child. If there is no right child, then the right child will be the sentinel node, and in that case we don't want to reset the sentinel's parent. The sentinel's parent should always be null. Does that make sense? Okay. So we handled, this is the case where there is no left child. Okay, so if there's no left child, we now ask, is there a right child? Okay, so we know we're at the point, so we kind of have this situation where we have the parent, and here's n. We know it doesn't have a left child. The question is, does it have a right child? That's the question we're now asking. Okay? So oh, by the way, if we get here, what do we know about the left? If we get to this point, is there a left child or not? Jaja, you're saying no. Or do you?
The left child is pointing to the center.
Okay, but is that really true? If we only get to this point here, if this condition is false. So we're right here right now. We're asking if n's right is equal to the sentinel node. So we only can get here if n is not equal to the sentinel node. I'm sorry. That's wrong. I'm confusing you. Take that back. We're right here. We only get to this point if n's left is not equal to the sentinel node. The left is pointing to something, so there is something there in the left child. Yes. So we know if we reach this point right here that there must be something in the left child. So the question is, what two cases are in play now? Is case one in play where n can be a leaf node? Mac, I'll ask you this question. Well, look at n. Can it be a leaf node? I know that the left child exists. Then no. So case one is out. Case two said that you could have potentially one child. Is that in play? Yes. And what about case three where it could potentially have two children? Is that in play? Yes. So the first thing we do is we need to distinguish between cases 2 and 3. So the first thing we do is we ask, is the right child the sentinel node? And Mac, I'm going to stay with you. If the right child is the sentinel node, do we have case 2, which is where we have just one child, or do we have case 3, where we have 2 children? Okay, so if the right child is a sentinel node, does that mean that the child exists or not?
No.
No. So if it's the sentinel node, it means there is no right child. So it means we must have case 2, where we have only one child. You're looking back and forth though, so
Well,
you're
I
not
thought
fine.
I thought it was the other way around. I thought it would, I meant the one child.
Okay.
Yeah.
Okay. So it is the one child case. So it's case 2. Case 2 is the one child case. So if we get to this point, so this is the case. If this is true, this is the one child case. And we have a left child. So this is our case. We have the parent, we have N, we know that we have a left child, but we have no right child. Okay? So in that case, we know that whatever's the root of this tree is going to get promoted. Correct? So we check, first of all, this code right here asks, is N a left child? Okay, if it is a left child, then we make the parent point to here. Okay, so, whoops. We're promoting the left child. So if it's a left child, we make the parent's left point to there. And if N was a right child, then we would make the right point to there. So it's whichever one gets, it's just promoting the left child up. Okay? And then we have to relink the left's parent. So in this case, we need to also make the left's parent point up to there. Okay, and then we delete N and decrement our size. Okay, and this is where logic becomes important. Okay, up here, we protect it. We didn't do this assignment if N's right was the sentinel node. But here, there's no check to see whether N left is equal to the sentinel node, because we could not have gotten to this point if N were the sentinel node. If N's left were the sentinel node, then this statement would be true, and we would have evaluated that block of code. So this is where you need to be careful with your logic. Okay, this is what I like about computer science. You can make logical deductions. You could not have reached this point in the code if N left were the sentinel node. So you know that it must be a regular node and that you can reset the parent. Okay? And finally, if we're not at case 2, then we must have this situation, parent N, and we must have both a left subtree and a right subtree. So this is case 3. So if you remember case 3, where we have 2 children, we have to find the biggest value in the left subtree. So that's what this for loop does, is it chases, it goes to the left. So the first thing it does is go into the left subtree, and then it chases this code right here, chase the right children until there are no more. Okay, the right child is always greater than the left child, so we always go to the right child for the greater value. And when there's no longer a right child, there can't be anything greater. Okay, so that's what that for loop is up to. Okay, so when we're done, MLC points to that rightmost child, that is the greatest value in the left subtree. So we save the information, save the info in MLC. What do you think MLC stands for? Since he's such a big fan, please don't do these abbreviations in your own code because it makes it hard to read.
Most left child.
It's actually not, what did you say, most left child? Oh, it's close. It's maximum left child. So he really, MLC stands for maximum left child. So he saves the info in maximum left child. That's what these two statements do. Then he deletes temp key. So now what he's going to do is recursively call delete on this particular key, and that will delete that child from the tree and do it appropriately. And then he sets ends, so he stores, these two statements store the info from MLC into N. Okay, why didn't he just say this? Why did he save the information in MLC? Why not just say N key? Why not just do this? It'd be so much simpler. Why not just say N key equals MLC key and N value equals MLC value? Because we deleted it, because delete blew away MLC. Therefore, that information no longer exists. So we had to save it first before we deleted MLC. Then we deleted it, and we were able to store the saved information. That was the hardest procedure. Okay, you may have to look at that on your own because I know it's not simple. Okay, so you may have to trace through that one. But any questions? Okay, so the remaining ones are easier. I'm going to first go through the destroy and the sort ones and do the print last. So when you destroy the tree, coming all the way back up here, let's say you destroy this tree. What you need to do is you need to destroy all of the nodes in the tree. Okay? So the general idea is what we want to do is kind of something like this. Let's say we have a node and we want to destroy it. What we're going to do is first call destroy on our left child, so it destroys our left subtree. Then we destroy our right subtree. And then we delete ourselves. So the idea is we're going to first delete our left subtree, then we'll delete our right subtree, then we'll delete ourselves. Okay, and we're going to take a vote on whether this is a pre-order traversal, an in-order traversal, or a post-order traversal. So all of those who think that this is a pre-order traversal, raise your hand. Okay? All of those who think it is a in-order traversal, raise your hand. A couple more. And all of those who think it is a post-order traversal, raise your hands. Okay? It is a post-order traversal. The reason it's a post-order traversal is that we first process the children and we process the node by deleting it last. If it was in order, the delete would be right there, meaning we would first visit the left child, then we would do the delete, and then we would do the right. And if it was pre-ordered, the delete would have been first. So pre-order, we do the computation first, then visit the left and right subtrees. In order, we do the left computation first, then visit the node and do the computation, and then do the visit to the right subtree. And post order, we visit all subtrees first and then do our computation. Okay? If we did the delete first, which is a pre-order, what would be the problem?
Lost track.
We lost the node, therefore we no longer have track of the left and right. The same problem with an in order, we would destroy the left subtree, okay, but we wouldn't have access to the right. So we need to do a post-order traversal. Okay, so going way down here, to the destructor calls a recursive destroy starting on the root node, which is the sentinel right. So call destroy, this is the root node. And then after we've destroyed the root node, it will be okay to delete the sentinel. So the recursive destroy does our post-order traversal. First of all, if it reaches a leaf node, it returns because we don't want to delete the sentinel just yet. Otherwise, we destroy our left, then we destroy our right, and then we delete ourselves. Okay, so fairly simple. Okay, and this stops the recursion. Remember, every recursive procedure has to have a base case. The base case is when we reach the sentinel node. Okay. Now, let's do the one with the sorted vector. So what that's supposed to do is return the values associated with the keys in sorted order. So if the keys are Fred, Binky, Alfred, Roger, Sarah, and Kyle, then we want to return them in the order Alfred, Binky, Fred, Kyle, Roger, Sarah, in alphabetical order. Okay, so you can see that what we're going to do is we first clear our array, then we call make vector on our sentinel node, or on our root, so that we call it on the root node. And again, this is a in-order traversal. So first we add all the nodes in the left subtree to it. Then we add Fred. And then 3, we add everything in the right subtree. So this is 1, this is 2, this is 3. So 1, recursive make, the first call to recursive make vector puts everything in the left subtree into the array. Statement 2 puts Fred into the array. Statement 3 puts everything in Fred's right subtree into the array. Hopefully you will agree that that results in everything going into the vector in sorted order. We call that an in-order traversal because the computation, which in this case was pushback, was done after visiting the left tree, but before visiting the right tree. So we pushed Fred onto the vector after visiting the left tree, but before visiting the right subtree. So that's an in-order traversal. Okay? And finally, print is kind of interesting. So print, what he was doing was going way back. When he printed, he always printed the root with no spaces. The two children had 2 spaces. Then basically your children are always indented 2 spaces more than you. Okay, so, and he's using what he calls a recursive reverse. I believe it is post order. Yes. No. There we go. I'm sorry, recursive, I'm sorry. It's a reverse in order. So what's going to happen is, again, if we have Fred, Binky, Alfred, Roger, Kyle, and Sarah, what he's going to do is a reverse in-order traversal. So what he's doing is he's printing the right tree first. The right tree goes above Fred. So the right tree goes up here. The left tree comes down here. And now if you rotate, that means the right tree would come down over here, the left tree over here, and Fred up there. So he is printing the right subtree first, then he's printing Fred, then he's printing the left subtree. So it's a reverse in-order traversal. So again, he starts by calling his print. There's no indentation, so that's the indentation level. It's actually the indentation spaces. And this is the root node. So if it's the sentinel, if he's reached a leaf, again he return. I'm sorry, if there's no child, he returns. Otherwise, he prints the right subtree. So print the right tree. Indent it 2 more spaces. Print myself. And finally, print the right subtree. Print the left subtree, I'm sorry. Print the left subtree. Indent it 2 more spaces. And one more thing, and I'll let you go. So notice this is an unusual print statement. He says printf star s. Normally, it would be something like %4s to say that the field should be 4 characters wide. The star allows it to be a variable width field, which is what we want, because for the root it should be 0 spaces of blanks. For the left and right child of the root, it should be 2 spaces of blanks. For their children, should be 4 spaces. So the number of spaces here is going to depend on the level. So in this case, the star says take the width of the field from that argument. And then he's saying print the empty string. So he's printing the empty string in a field of some width. So print empty string. Print empty string in field of width level. And because it's 0 characters, the empty string is 0 characters, it's going to be padded with level spaces. So it produces the right outcome. Okay, I know there was a lot to absorb today. This would be a good lecture to go back and review. I will be posting this lecture online, and you may want to go back at some point and review it, because you're going to be writing code on the final in 2 weeks in the in-lab, and it's going to be involve binary search tree code of some kind. So you really need to understand this code. So I would